Anyway, we learn about these other ways of expressing apart from y equals mx plus b, slope and intercept form. That's one way. We also learn about the vector equation, the vector format for presenting a straight line. We learn about the parametric. And we were also learning, and the thing about the vector form and the parametric form is that the truth is that there could be more than one way of representing a straight line with the vector and parametric form. But then we learned that there is a Cartesian equation, which, by the way, is the same thing as the standard form. And that's why they call it standard form for a straight line that you learn in grade 9, which is exactly also a vector concept. But with the standard form, you don't have 4 or 5 different ways of, or in fact, an infinite number of ways of presenting the line. There is really one way of presenting that line. Right? In fact, if it turns out that the A, B, C of those coefficients are, can be reduced, then you should reduce it. Okay. All right. So here's what that looked like yesterday. All right. So I'm doing a bit of review now. We took an equation that looked like this: x equals 2 plus 3t. These are the parametric equations. We isolated them to make them symmetric like this, set them both equal to t and then make them equal to each other. We cross multiplied and this is what we ended up with. Okay. All right. So next page. Right. A line has this vector equation. We did that. Find its Cartesian equation. So I went through that process with you. Right. So here's the here's the vector equation, and we put it in parametric form. We set it equal to, we isolated the t, went through all of that, ended up with this here. So 3x plus 7y minus 29. Now, you're asking about the shortcut method. If you go back and look at the original function, you'll see the 7 and the minus 3 here, which looks a lot like the 3 and the 7 down here, except it's been reversed, and also it has changed sign. It's almost as if you're saying that if you took the 3 and the 7 and made it into a vector, that what you would get from dotting both of these two things, this is the direction vector for the line, that you should get 0. Look at that. It was 7 minus 3, and down here it's 3 and 7. So it means that and this is not just a coincidence in this particular case. And I made that point yesterday. This is a consistent thing that you will find. In fact, what is happening is that this 3 and this 7 would represent the normal vector to the line that you're looking at. And normal, remember, means that it is at right angles to the line that you're looking at. So if I wanted to get a vector which was at right angles to, or a vector, yes, which was at right angles, I take the 3 and the 7 and I would reverse them. And I would change the sign. This is really a negative sign right now because we have one positive and one negative. So if I were to reverse, I make them both positive. And that's exactly what's happening here. To get the minus 29, what we did here was we took one of the points, or the point that we have, the minus 2 and the 5, and we plugged that in. So if I were to plug in minus 2 for the x and the 5 for the y, and then there's a c on the end, or plus c on the end, then solve for the c, that c would equal to minus 29. Okay, Azia, I think there's another example of that coming up, if that is helpful for you. Okay, representing the Cartesian equation line in vector and parametric form, determine the equation vector. Okay, so do we need? All right, let's see if we can find. Okay, here's another one that we did yesterday. For the line with this, determine the equivalent slope intercept form. That's not hard at all. Right? If you think about that, this again represents really what the slope of this line is. This minus 1 and 4, the y over the x, really represents what the slope of the line is. So it's really a slope of 4. But then if you wanted to go through the process of creating the parametric equations and then setting them both equal to t, and then cross multiplying, you still end up with this, right? This is, of course, the standard form of it. But then if you were to, actually, that's the standard form of it. If you were to rewrite this, you get the y equals 4x, I guess, minus 18, which comes from knowing that this is really the slope of the line. So there's a shortcut to this one as well, all right? And I'm going fairly quickly because we did all of this yesterday already. determine the Cartesian equation, Cartesian form the line with the equation. And this equation, notice now, is, well, tell me about what this direction vector is telling you. Anybody? This direction vector 0, 2 is telling you what? What kind of vector are we talking about which has a direction of 0, 2? Right? What does that suggest to you? What kind of line are we talking about? On the y-axis, or it's a vertical line, is what you're saying. Right? That's really what we're saying. It doesn't have to be on the y-axis, but it is a vertical line, right? Okay, because this vector is a vector which runs from 0 up to 2 and doesn't go across, it's a vertical line, right? And then it, of course, goes through the point 1, 4. So we should be able to come up with an equation for that fairly easily. Again, I'm not going to do this right now. If anybody wants to come back after class and go over that with me, then we can do it. Okay, determine the Cartesian equation passing through that, which has that. Okay, I wonder if we could figure out this one, right? I'm going to stop for a minute and do this one. It says that the line passes through this point. It has a normal vector of 5, 3. What might that tell you if they're telling you not the vector, which is the direction vector, but the normal vector, right? So what do you think the Cartesian equation might look like? Well, is in fact going to, well, yeah, that's fine. But if I'm writing the Cartesian equation, shouldn't I just use the 5 and the 3 then? Isn't that the case? You remember what we said before? Let me take you back again. The 5 and the 3 is a normal, right? Let's go back and have a look at this one that we did before. That was this one here, right? The 7 and the minus 3 represented the actual direction vector for this function. But when you put it into its Cartesian form, then the 3 and the 7 get reversed, and then they become in a sense, the normal, right? So if I now give you the normal, right, let's see if you can follow me on this now. All right, this is the actual direction vector, 7 minus 3. But when you put this into the Cartesian form, it becomes a 3, 7. And then we have to figure out the minus 29. So let's see if anybody can tell me where to start with this one then. Where was I? Yeah, this one here. What do you think? This is the longer method. Can we first get the y equals mx and convert that to... This is the shorter method I'm actually showing you, Daria. We can, tell you what we'll do. We'll do both, right? We'll do both, right? Let's first of all, I'm gonna tell you what my answer is first of all, and then then we'll go through the longer method, right? Because I consider that to be the longer method. So what I'm going to say is this: the vector that I'm looking for, the equation line that I'm looking for is actually 5x plus 3y plus c equals 0. I use the actual normal as the coefficients of the y and the x. And now we're going to see if we can find, you don't see the example in my whiteboard. I didn't do a whiteboard for this, Zia. Okay, I don't have this on the whiteboard at all. I didn't do a whiteboard for this at all. Let me continue. So this 5 and this 3 is the normal. So I'm just putting this 5x plus 3y plus c. I know we have to find what the c is equal to 0. And how are we going to do that? We're going to plug in the 4 and the minus 2. Okay, so 5 times 4 plus 3 times the minus 2 plus c equals, we'll do it the other way as well, right? We'll do it the other way as well. So just hang on with me on that, okay? So that would be 20 minus 6 plus c equals 0. So 14, excuse me, plus c equals 0. So c is equal to minus 14. Okay? So I'm therefore saying that the equation is 5x plus 3y minus 14 equals 0. But why don't we now go through this long way, through the long way? So first of all, if the normal is at 5, 3, let me come down here now. So that's an answer that we're going to be putting aside for now. Give me what you consider to be what would I use as a direction vector for the actual function is what I'm saying, right? So we know that one point is at 4, 2, so xy is equal to 4 minus 2, sorry, plus t times, we're going to put the minus 3, 5. Yeah, minus 3, 5. Now, this might, what we're doing now, might prevent us from getting too far with the stuff I actually had planned for today, but that's okay, right? We'll do what we can. 3, sorry. 3, you put minus 3, 5. Yeah. Let me just erase this whole thing. Okay, so my question for everybody in the class, Daria gave us an answer, but is everybody comfortable with this as the vector, which would represent something which has this point or goes through this point and has this as a normal? Normal, of course, remember, means that it is at right angles, right? So this is at right angles. So if I were to multiply this 5, 3, by this minus 3, 5, I'll just do that on the side over here, and I'll erase it afterwards. So if we multiply the minus 3, 5 by the 5, 3, right? 5, 3 was the one that they gave us, and we're using minus 3, 5 as a direction vector. Confirm for yourself very quickly in your head that this is going to give us a dot product of 0. Can we agree on that first of all? Yes or no? Let me hear from the class on that. Can we agree on the fact that those two give us a dot product of 0? Perfect. So I'm using that as my direction vector. Let me erase that. And what we're saying is that this direction vector would be at right angles to this thing right here. Okay, so let's go through the process now. Let's go through the process. So x is equal to 4 minus 3t. Y is equal to minus 2 plus 5t. Okay, please stop me if at any point this isn't making sense. All right, so I'm going to isolate my t now. So I'm going to say that x minus 4 divided by minus 3 is equal to t. And I'm going to do y plus 2 divided by 5 is also equal to t. All right, let me do a quick room check here just to make sure that we're all following along on that. Sarah and Zia. Sarah and Zia. Let me hear from both of you on that. And Zia, how about you? And does it make sense? So you're checking in, that's good. But does it also make sense what I've done? I want to make sure the steps from yesterday make sense. Okay, and Sarah, you're okay with that as well? Okay, perfect. So what this means is, just erase that part right there. Is that I can now set them equal to each other. So x minus 4 over minus 3 is equal to y plus 2 over 5. Okay, I'm setting them equal because they're both equal to t. Okay, the symmetric version of the equation, they're both equal to t. So I can cross multiply now. So my 5x minus 20 is equal to my minus 3y minus 6. I want to say that that is right. Minus 3y minus 6. Yeah, okay. All right. And now I'm going to just put everything together as 5x plus 3y. The minus 20 plus that is minus 14 equals 0. Now, how does that compare to what we had before? Let's just have a look. 5x plus 3y minus 14 equals 0. 5x plus 3y minus 14 equals 0. So what we're saying is, if they give you the normal, you're off to the races, right? Because the 5 and the 3, without changing anything, it's going to be the 5, which is the x, and the 3, which is the y, that we're going to use, along with some c that we don't know yet, but then we have a point that we can use to figure that out, is how we're going to get the equation, the Cartesian equation of the line. So my Cartesian equation, so if you were ever asked what is the normal to this line, I would just say it's 5, 3. what would the vector be that would be a normal to this line that I just wrote here? It'll be 5, 3. Right? The 5, 3 vector is a normal to the 5x plus 3y minus 14 equals 0 Cartesian equation. All right? I just want to make sure that everybody is fine with that, right? So when I asked you initially to give me, and you asked for the long way to do this, by the way, Daria. So I went through what I consider to be the longer way to do this, but got the same answer. The shortcut is take the normal vector and use those numbers to be your coefficients of x and y and figure out your c, and you're done. So let me check in with Daria first on that. Daria, does that method make sense to you, what we just did? What I was saying is to find the b using, oh, okay, okay. All right, so let's see then. But if I'm answering the question about Cartesian, during the term of the Cartesian, which has that, you could do that as well, right? But and convert, yeah, we could do that, and then multiply it through by the thing. Yeah, that could work as well. So what Daria is saying, okay, and convert to, yes, you could do that as well. So what Daria is saying is you could use the actual vector, which would be the minus 3, 5, and you could write it in y plus mx plus b format, then multiply through by whatever is going to clear all of those fractions, rearrange it, and you get your Cartesian form. But I honestly think that this is, if they give you the normal, if that is what you have, I think your job is a lot easier. And if they don't even give the normal, if they give you the original vector, so let's say they said that the position vector was whatever it was, you can just use that to create the normal and you can write your equation, right? I just think that's the easiest way to do it rather than having to go through y. I know you're familiar with y equals mx plus b. You did that from grade 9. But I also think, and I mean, it's up to you as to how you want to approach this. I also think that there are some more efficient, shorter ways for you to get through this if you understand that the normal to the line will represent the coefficients of the x and the y for the Cartesian version of the equation. If that's what you're after, the Cartesian version, then knowing the normal gets you to that point a lot faster. Is everybody clear on how I could use the normal to get that final? I want to be sure about that. Does everybody follow that methodology, right? If you have the normal, how you could use the normal to get the actual final Cartesian equation. Does it make sense? I need to know. I'm not hearing from anybody, so I need to know. Does that make sense? Because I can do it. Okay, Renee, thank you, Renee. At least Renee says, and Alex and Lily. Okay, perfect. All right, I need to get that kind of feedback because I don't want to rush faster, go through this faster than people are understanding it. Why does using normal work? Well, here's the thing about math, Zia, right? It's what's called pattern recognition is a big part of math, right? If you see a pattern which consistently links your destination, right, with the method that you are using as your pattern, then continue to use it. What you're noticing is that the normal, and it's a matter of looking at what happens to these components as you work your way through this. The normal always works out to be the coefficients of the x and the y. Let's just put it in those terms, right? That if you look at the pattern of how the normal shows up in the final equation, it is a shortcut. One of the things I said to you when you were doing the hanging picture or whatever it is with the two cards and the tension in the two wires, was it Sharujan who came up with the shortcut? I need to remember who that was. Was that Sharujan who said that, hey, listen, I found the shortcut? Oh, Zia. Okay, Zia, thanks. So Zia said, you know what? We found a shortcut where you can just use these numbers, right? Add them up, and then take the not the supplement. What's the other word? Complement of the angles, and then use that with in your sine law, and you get your answer. So now I was saying this to you as we were doing this. There's also a shortcut that you could use if you're using the method of the components to see where things end up, right? If you can see that relationship between where you start from and the final calculation, then you can cut out some of those middle steps, right? And that's what I call pattern recognition. Math is all about how do you see the pattern from going through a series of steps, an algorithm, so that you don't have to go through all of the algorithm steps itself, because some things end up in certain places all the time. Okay? All right, so that's how I'm going to state that. And I think the only other thing I want to do from yesterday's class is, do I really want to talk about this? Show that these lines are parallel and non-coincident. I'll mention this. Excuse me. So we have two equations of lines which are in Cartesian form. 3 minus 4y minus 6 equals 0, and the other one is 6x minus whatever equals 0. They're parallel, but they're non-coincident. What do you think would make them parallel, right? Let me ask you this. Same slope, good. But what about if they had the same normal, right? Would they also, if they both had the same normal, excuse me, would that also suggest that if two lines are parallel, that their normals would also be parallel? So I'm looking at this 3x and minus 4y, and I know what the normal is to this. It would be 3 minus 4, and this one is 6 and minus 8. And wouldn't it also suggest that the normal for this, if the two normals are parallel, or if they're the same normal, and in fact, you can look at them and you can tell, right? So I don't want to spend a lot of time on this. You can tell that these are both normal. These two normals are the same, because multiplying this first one by 2 gives us the second one. That's hopefully very clear, right? And so 3 and minus 4, just multiply that by 2 to get the 6 and the minus 8. That does suggest the same normal, which is the same slope, right? Remember, I'm not talking about the slope of the actual line. I'm talking the normal to the line. And that you can get from just these coefficients here. But the multiplying this by 2 makes this become minus 12, whereas this one is positive 12. So that is how we know they're parallel from the slope, but non-coincident because the constant part of this isn't the same. If it was the same constant on the end, this minus 6 was, let's say this was minus 12, then we would know that in fact they were not only parallel, they were actually the same line, right? Just multiplying a thing by 2 doesn't change the line. What does non-coincident mean? If they were coincident, it means that they were the same thing, right? So they were just the same. You remember when you were doing intersections of lines? Let me take you back to grade 10 maybe. And they would say that two lines would intersect if they had different slopes at one point. If they were parallel, then there would be no point of intersection. Or if they were the same line, there would be an infinite number. I don't know if you remember this from grade 10. I think this is grade 10 that you did that. And if they were the same line, then you would have an infinite number of points of intersection. If they were the same line, that would mean that they're coincident. They're really both the same thing, right? You just multiplied one. Oh my goodness, I need some water. Give me a second, please. Yeah, if you just multiplied one by some number, it will become the other. And that's all that was. Okay. Now this one is talking about two lines being perpendicular, value of k so that these lines are perpendicular. So again, without me actually going through the process, what you're thinking is if they're going to be perpendicular lines, then their normals should also be perpendicular. And all I would do is I would take these two normals and I would try to find a number which would make their dot products equal to 0. I'm not going to go through that. Again, if you want to work through that with me one-on-one, then please do that. We're already at 2:04. Let me go on to the last question, which we started but didn't finish. Excuse me. And if I'm going too fast for anybody, I just like how Zia stopped me a few minutes ago and asked the question. I want the rest of you to do the same thing, right? Always feel free to ask me to slow things down and ask for clarification for anything. And that's why I like when students like Zia and Darren, and I don't want to call any more names because there are lots of students who have been doing that. So I encourage you to continue doing that. Right? And if we need to leave stuff out because we want to focus on the things that we've done and make sure you understand that, I much prefer that. It's not quantity, it's quality for me. All right, get back to this question now. Excuse me. Determine the acute angle formed at the point of intersection created by the following pairs of lines. And they specified acute angle because if you think about it, two lines intersecting will form two angles. Could be on this side over here where I'm pointing to right now. But if you were to extend these lines, if you were to extend these lines, there'd be another POI, another angle that would be created, which should be more an obtuse angle. So they specify that it's going to be an acute angle. So what we're doing is looking at the pair of lines, right? So they have both direction vectors at -1, 3, and 3, 4. And we took them and we used that angle formula that we learned back in the second unit, I think it was. We dotted the two vectors, the -1, 3 and the 3, 4. And then we put that over the magnitude of the two vectors. So we'll just finish this very quickly then. So that's, what is that? -3 plus 12, which is, I guess, 9. I'm going to say that's 9. And please help me if I, correct me if I made a mistake on that. And then the magnitude of the vectors is the square root of 9 plus 1, which is 10, times the square root of 25. Okay. So theta is equal to cosine to the -1 of whatever this is, 9 of the square root of 250. Notice that I just multiplied the two things on the bottom, because if I'm multiplying two square roots, then I can multiply by the product of the radicands, the number under the square root. So I need some help. I can't do that in my head, so I'm going to turn to one of you with your trusted calculator, 55.3. Thank you, Baroka. So approximately 55.3 degrees is the answer that we got. And I don't hear anybody objecting to that, so I'm going to assume that Baroka is right. Okay? Everybody else on board with Baroka's answer before we move on? Did you all get the same thing? Have you tried this for yourself? Thank you very much. Appreciate that. All right, so what I'm going to do now is I'm going to head over at 2:07, which gives us approximately 32 minutes to see if we can get through as much of 3 space as possible so that you can get that homework done. And so let's see now. That should be this one here. I'll save this. All right. The great thing, though, is that once you've understood 2 space, then 3 space should be easier. And I'm going to be able to answer the question, I think, that was asked of, I'm going to say it was Daria who asked this question. When we're looking at the equations of some various axes, and looked at the x-axis and the y-axis, and we talked about the x-axis being the same thing as the y equals 0 line, and the y-axis same thing as the x equals 0 line. So that was 2 space. And then he asked, so what's the equation of the z-axis? I think it was you. And I said, okay, hold on to that question for a little bit, because we're going to look at equations of lines in 3 space, and we'll need that for us to be able to do that. So now we're in the 3 space environment and we're looking at equations of lines. We now have a little better understanding of how we can put that together. So let's see if we can answer that question in a few minutes. So there's your learning goal. And we learned that we can express lines in 2 space using vector, parametric, symmetric, and Cartesian equations. So is it the same thing in 3 space? Well, in 3 space, the lines are turned by a given point and a direction vector. So we'll now investigate each of these forms and how they relate to 3-dimensional space. And it is what you think it is. It is what you think it is. So as with 2 space, you have a position vector, and it can be drawn from the origin. And then when you add that to another direction vector, you get the vector form of the equation. So here's a line, right? Sorry, here's a point on the line, and here's the direction of the line. So here comes the vector form of the line. I'll use r this time rather than using x, y, z, and that is equal to the -5, 2. There are 3 components to it this time. We're in 3 space now, and we're going to add on to that, surprise, surprise, some scalar, some parameter times the direction vector 1, 4, -2. It really is just adding one new component to the 2 space version of the line, the vector equation in 2 space. So what does it look like parametrically? Well, again, that means that x should be equal to the 3 plus t, and the y should be equal to exactly what we did yesterday, the -5 plus 4t. And the z should be equal to the 2 minus 2t. It's exactly what you expect. And if we isolate the parameter, which is to say what t is equal to, then t is equal to each one of these things. Excuse me. It's equal to the x minus the 3 divided by 1. Really don't need the 1 on the bottom, but we'll put it in anyway. And that should be equal to the y plus 5 divided by 4. And that should be equal to, again, this is the z now. We're just taking each one of these things and we are isolating the t. And because we're isolating the t, it means that since they're all equal to t, we can set them equal to each other. And that would be equal to the z minus the 2 divided by minus 2. Okay, so far, hopefully, so good. T is equal to all three of these things. Now, the last time, what we did is we used any two of them and we came up with the Cartesian equation. That's what we did the last time. Don't be tempted to do that in 3 space, right? There is a Cartesian equation. Sorry, there is no Cartesian equation. I said it the wrong way. The equation that you're thinking that might work by, like, cross multiplying these things, and maybe you have a something x plus something y plus something z, is not the equation of a line at all. It's the equation of a plane, which we hopefully will get to tomorrow. Okay, it doesn't give you the equation of a line by doing that cross multiplication that you would expect. So let's answer Darius' question now, right? He wanted to know what the equation of the z-axis was, right? In fact, it would apply to the x-axis and the y-axis also in 3 space, but let's just focus on the z-axis for a minute. What do you think would be the equation of the z-axis? Well, look at this. It's r equals, r, the vector r that is, it's in vector format now, is equal to a point on the line at 3 minus 5, 2, plus t times some position vector, which, remember, position vector is taking a line from the origin out to some point in space, which has these coordinates, 1, 4, minus 2. So what do you think then, folks? This wasn't part of this slide, but I thought we'd return to it because it was a good question that Daria asked a couple of days ago. I forget when it was. Right? So what would that line, so this is for the z-axis now we're talking about, z-axis. And remember that it isn't one unique equation, right? This equation that we just did here, right? It's only because we had these, we have this direction vector, and that direction vector, by the way, could be a different direction vector by just simply multiplying these all by -1, right? And I'd have -1, -4, and +2. That would be fine. So there you go. All right, so 0, 0, 1, you're saying, so t, or not t, I'll use a different letter, I use r again. So r, vector r, would be equal to, he has 0, 0, 1. The truth is, Daria, I could have used 0, 0, 0, right? Just saying, because 0, 0, 0, the origin is on that axis as well. Right? But I'll use a 0, 0, 1 because that certainly is a point on the line, plus t times, I would really just use the k vector. The k vector, as you remember, the k basis vector that is 0, 0, 1. And of course, you could change that to make it 0, 0, 2, 0, 0, 9, whatever. That will just depending on the value of t. I'm a little confused how we got the equation. Oh, remember now, think of the format of all 3 space lines. It is a point on the line, right? Plus, it's just like with 2 space, plus some parameter times the direction of the line, So far, so good, Zia. Look at the first example. Does that first example make sense? Right? We had that this m was a direction, and this point is on the line. So we added the point to the direction vector, and there was our equation of the line. All right. Now, we're trying to get an equation for the z-axis. Well, think of the z-axis. There are lots of points on the z-axis, right? The z-axis, remember, is a line that goes straight up and down, right? So every point on that line, there are lots of points on the line. One of the points on the line, and the one that was chosen by Dario, was 0, 0, 1. I made the point that we could have used 0, 0, 0, to be quite honest, because that's on the line as well. But we'll use 0, 0, 1. Can we agree that 0, 0, 1 is on the z-axis? Can we agree on that, Zia? Perfect. So that would represent a point on the line plus t times the direction vector for the z-axis. Just think of the z-axis. Z-axis is just a line that's going straight up along the z-axis. It's not going along the y-axis. It's not going along the z-axis at all. So it has zeros in both of these positions right here. And it's just this. So it's just t times 0, 0, 1. Do you see what we're saying there? The direction vector. It could have been 0, 0, 2, absolutely. Remember that it's not a unit. In fact, to get that 0, 0, 2, I just use the t value as being 2. Because I would just take 2 times all of these. Those are still zeros. And then this would become the 2. So yes, you could use 0, 0, 2. You could use 0, 0, any number you like. In fact, even a negative number would also work. Because that just is what would become the result of taking the t to be different values of t. Different values of t will give you different points along that z-axis. All right? So is there no way to give the equation of lines in 3 space in standard form? No, not, well, again, I'm going to say not that I'm aware of, right? If you're looking for a standard form, you might think it might look something like the Cartesian equation in 2 space. And I'm here to tell you that any equation that has, like, for instance, 2x plus 3y plus 4z plus some constant equals 0, something like that, that's actually not the equation of a line, it's the equation of a plane, which I'm hoping we're going to get to tomorrow. All right, we'll talk about how we get that equation tomorrow, of a plane, not of a line, but of a plane. So I'm not aware of a standard form. Yes, we have the vector form, we have the parametric form, we have the symmetric form, we have those 3, but not a standard form. So if you give us a question like this on the test, you could expect to give our answer how you gave it. Yes, Shrujan. That's actually a good point, that there are different forms that you could come up with this. But if the information I gave you was this, that this was this point on the line and that was the direction vector, I would expect that the answer that you'd give me would be this answer right here. What I could do also, Sharut, is give you some other point and say, is this point on the line, right? And I'm hoping that you know how to do that, right? If I gave you a point, I said, just arbitrary point, 7, 6, 24, something like that, I just made something up and tested you and said, determine whether this point is on the line. I hope you know, and I just say it out, and then, hopefully if I give you a question, you know what to do, is I would take, let's say what the x value of that point is, solve for t, and then see if that t will generate the other 2 components of that point that I'm looking to see whether it's on the line, because every other component must match with that same value of t for me to know whether that is on the line or not. Okay, let's continue. We're at 2:19 already. We're about 21 minutes to go. So let's see if we can get most of this done. Sorry, somebody has a question. I heard a mic just unmute a while ago. No? All right, let me continue then. All right, find a vector, parametric, and symmetric equation for the line defined by the point. And here is the point. So this is just simply, it was me joining. Oh, okay. So this again is nothing which should make anybody stumble. Here comes my vector form of the equation. So vector, parametric, and symmetric for the line defined by this. So here's my point. So my point is at, so I'll put R with the R on top. I could put the X, Y, Z as well. That's fine. And that would be equal to the point, the 4 minus 1, and the minus 2. Oh, by the way, there is something, oh, that's ugly. There is something that I hope you'll notice about shortcuts, which I keep stressing is something that you should be doing. And I'm going to see if I can make that point on this one. So here's the point on the line, plus t times the minus 5, the 1, and the minus 3. Okay, so there's your vector form of the equation. The parametric, excuse me, the parametric would be that x equals, let me come up some more here. Yeah, everybody should be good at this by now. That x equals the 4 minus 5t. My y is equal to the minus 1 plus t. And my z, I'll put that over here. And my z is equal to the minus 2 minus 3t. Okay, so that's the parametric. Now the symmetric, remember, is when you isolate the t. So I'm hoping you're going to accept this. So I'm going to have the x minus 4 divided by minus 5 is equal to the y plus 1 divided by 1. Really don't need to put that in, but I put it in anyway. And that's equal to the z plus 2 divided by minus 3. Now, it would be useful for you to note, excuse me, there's an obvious connection between these values here and the symmetric form. The constant is the thing you subtract. Well, let me say that a different way. The constant, the opposite sign of the constant is what you add or subtract to the x. So if this is a positive 4, then it becomes x minus 4. The denominator becomes whatever the coefficient of the t is. That's why that's minus 5. Same thing here. Opposite sign of the minus 1 becomes plus 1, dividing by the coefficient of t, which is 1. And same thing here. The minus 2 becomes positive 2, and this becomes divided by minus 3. So if you had to go the other way, that shouldn't be hard at all. If you had to come up with the parametric equation, then you just reverse the order of this, right? You'd first of all use this to multiply by the t, the denominator, and then you put the opposite sign on whatever it is that you're doing with the x or the y or the z. So hopefully you can go in the opposite direction on that one. Okay, let's move along. Find the equations in each form for the line that passes through this point and is perpendicular to both this and this. Now let's talk about this for a minute. And I'm going to use some terms that will hopefully jog your memory on this. I'm not just looking for a line that's perpendicular to the 3, 2, and 5. I'm not just looking, Daria is way ahead of me on that. I'm looking for one that is mutually perpendicular, meaning it is perpendicular to this line and also this line, right? So I have two lines, right? They probably cross each other at some point, and I'm sorry, we're not going to get to intersections of lines in either 2 or 3 space. You did intersections of lines in 2 space back in grade probably 10. But there is a way to do intersections of lines in 3 space as well, but we're not going to get to it. But at any rate, we have these two lines. They're not coincident. They're not parallel, right? And so we're saying, can I come up with a line which is perpendicular to the 3, 2, 5 and also perpendicular to okay, this is in parametric form now. Not parametric, sorry. This is in symmetric form over here. So is there a way to do that? And look at what Daria just said. He's absolutely right. We put the cross product. It would be the cross product. So the direction vector for this and the direction vector for this need to be crossed. Not dotted, but crossed. Dotting would only tell you that two lines are perpendicular. But if I'm trying to find a third line, which is mutually perpendicular, so it's perpendicular to this and perpendicular to this, I need a cross product. Daria is spot on that. So what is my first direction vector? Well, my first direction vector is the 3, 2, and the 5. What am I crossing that with? What is a direction vector that would come from this? Bear in mind what I just told you, folks. Bear in mind what I just told you. Where do I look on this thing for the direction vector? So X, this is the symmetric form, right? So you're saying 2, 6, and minus 1, the denominators. In fact, I'll take you back to this previous page. And this minus 5, this 1, and this minus 3, if you look at the direction vector, just focus on the direction vector for a second. Those are exactly the same numbers. There is a minus 5, there is the 1, and there is a minus 3. That was these denominators are your direction vectors, right? So if this was just x minus 4, by the way, and if this was just y plus 1 and there was a denominator of 1, you have to put a 1 in there, right? So that means that we're going to use the same principle here. The cross product is going to be with 2, 6, and minus 1. Exactly what Quinn just said. It is, in fact, the denominators that we're going to use because the result of crossing both of these will be a vector that represents a mutually perpendicular direction vector to these existing direction vectors. Let me pause because I want to let that sink in here. I want to be sure. Scott, how about you on that? Neil, how about you on that? Scott and Neil. Let me hear from Scott. Let me hear from Neil. Okay, Scott, so you're good with that so far? And Neil says, okay, great. So that's good. All right, so if everybody understands that, let me go back now and remind you how this cross product thing works. This is Kamuk style, by the way. Some of you still like to use the other method. I saw that on the test the other day as I was going through your various steps, and that's fine. Nobody is forcing anybody to use any particular method, but I like this method using, it's really a matrix method. So I'm putting the 3, the 2, and the 5 there, and the 2, the 6, and the -1 here. And if you remember, I'm putting my hand over the first column right now. So I have -2, excuse me, -30, which looks like -32 to me. For the first number, putting my hand over the middle column now, and I'm having -3 minus, this looks like 10, and that's -13. But I'm going to make it +13. As you remember, you have to change the sign for the middle number. That's how matrix multiplication works. And to get my K value now, I'm going to use, I'm literally putting my hand over each column as I go along. To get my K value, I'm going to get 18, and I'm minusing 4 from it. 6 3 is 18 minus 4, which is 14. So my cross product is equal to -32. Unless anybody got something different, by the way, you can certainly check for yourself. That's the cross product I'm getting. Could you just double check that on your end for me, please? And let's see if everybody else is getting the same thing. Do it for yourself. Don't wait. Don't depend on me, folks. It's good that you can do this for yourself. So go ahead and check that for yourself. And can I get somebody to confirm that they got the same thing? At least one of you to confirm that you got the same thing. You know what? If Lily says she got that and Baroque can, okay. So you know what? I think I'm good now. Thank you very much. Yes, perfect. Okay. So now we have this as the direction vector for the line that is perpendicular to both of these. So what's the equation going to look like? What's my R going to look like? Well, it's going to look like a line that passed through 7, 3 minus 4 and has the direction vector given by this. Okay, that's it. That's it, that's all. So the key to this question is to understand that you're looking for something which is mutually perpendicular to two pre-existing vectors, right? Which vector could I come up with which is at right angles to the 3, 2, 5, and as Quinn pointed out, the 2, 6, -1, because these three denominators, don't you also have to put it in each form? Does it say that? In each form? Yeah, okay, all right. Okay. Thank you. Thank you, Sharujan. Thank you for spoiling. I was hoping to just go on and do the last thing, but no, you're right. You're right. I'm not. I'm being sarcastic. So x is equal to 7 minus 32t. Excuse me. And my y is equal to 3 plus 13t, and my z is equal to -4 plus 14t. Okay, and then putting it into symmetric form now. Remember, there's a shortcut for this. So that should be that I should have x minus 7 divided by -32. All right, hopefully that makes sense, is equal to y minus 3 divided by 13 is equal to z plus 4 divided by 14. Okay, thank you, Sharujan, for keeping us honest on that one. We should do what the question asked, and so I've done it. All right. Okay, so we're at 2:30 now. Let's see if we can get through. Maybe I think it's one other question on here. Or is it two more? Let's see how many more questions we had on here. Geez, okay. All right, let's get to this one. Determine the vector and parametric equations, just those two, for the line that passes through 2 points. So they give us 2 points now. They didn't give us a direction vector. They gave us 2 points. So how am I supposed to do that? I don't have any direction vector. I just have a point. Sorry, I just have 2 points. So help me out, folks. What do you think? Come on, I need some feedback from you on that. What do? I only have points. Head minus tail. Yeah, I wouldn't call it a distance equation though, but I know what you mean, Quinn. It's really not the distance equation. It's the vector that comes from subtracting. Yeah, right. It comes taking p minus q or q. It doesn't really matter which way you do it because the direction of the thing doesn't matter for this at all. The t will always give you different points along the line. So p minus q, q minus p, I don't really care. I'll go with the p minus q for no particular reason, right? So if it's p minus q, then I'm gonna go. So this is the p. What am I doing now? P minus q. So that would be the qp vector then. I'm just gonna go with pq. Okay, so that means I'm going to have head minus, so minus 2 minus that would give me 0. 4 minus 3 is 1, and minus 1 minus 5 is minus 6. Square for vectors. So there you go, folks. There you go. That would be the, and let me just double check that. Minus 2, 4 minus 3, minus 1 minus 6. Yeah, so there's my position vector. So I'm now ready to write my vector equation. R. Oh, there's something I haven't been doing. I haven't been saying that t is an element of the real numbers, and I should spat myself on my wrist for that. I really should be doing that. That's bad form. Anyway, so here's my. Oh, by the way, which point should I use again? Which of the 2 points should I use? Can anybody help me out with that? Anyone? That's right. So again, there's that flexibility. So minus 2, 3, 5 plus t times the position vector 0, 1, minus 6, and t is an element of the real number set. Okay, it doesn't matter. Thank you, Alex, and thank you, Sharujan. And that's it. It's really not anything more complicated than that. Okay, let's get to, let's see, 5 and 6, right? So we can line pass through the points. Oh, why would I need to do that again? We just did that. We don't need to do that again. Right? Oh, the symmetric equations. Yeah, well, whatever. All right, let's get to number 5. Show that the following are vector equations of the same line. Okay. How do I show that? How do I show that this minus 104 plus s times this as one equation of a line? Show vectors are collinear. So that's a starting point, right? So the vectors are collinear. But if the vectors are collinear, that doesn't mean that they're the same. Excuse me, that they're necessarily the same line. We also have to show that the point on one can be found on the other. That's also important. So Dario makes a good starting point. I could have 2 collinear vectors though, as direction vectors, but I'll give an example of what I mean by that. Right. So here is a direction vector that looks like that. Here's another direction vector. Right? They're both same direction vectors, but this one may pass through the origin. This one does not pass through, but they're still the same direction vector, right? So for us to show that they're the same line, not only must they share direction vectors, they must also share the points that they have on them. So I have to be able to show that the point on one is on the other or vice versa. Right? If I can show that, let's say the point minus 104 is on, first of all, establish that they're parallel, right? Or collinear, as Darius said. Establish that first, and once you've established that, then you have to see if you can take 1 point from one vector, one line, and see if that point can be found on the other line. That's how we would show that they're the same line. So we're going to try that right now in the 5 minutes that we have left. So first thing is, are the direction vectors the same, right? Is one vector, the minus 1, 2, 5, and the minus 2, 4, 10, all right? Can we say that those 2 direction vectors are really collinear direction vectors? Is there any way for us to show that? Right? I'm asking that question. Is there any way for us to show that those 2 vectors are, there you go. If I just simply multiply, thanks Alex. If I just simply multiply the first one, so 2 So 2 times the minus 1, 2, 5, right? If the S value was 2, then that's going to give me the minus 2, 4, 10, right? So all I need to do is scale one vector and it becomes the second one. Alex and Daria are both right. Okay, hand going up. Let's see who that is. Go ahead, Zia. Yes, 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 I agree with that. So the other way that we could do this is see if the ratio of the x's is equal to the ratio of the y's equal to the ratio of the z's. What do I mean by that? Putting the minus 1 over the minus 2, putting the 2 over the 4, putting the 5 over the 10, they all give you the same ratio of a half. And that's, again, also proof positive that you do have vectors which are basically what I will use the word that Daria mentioned. They're collinear, right? As position vectors, they're collinear. Okay, fine. But are they the same line? And here is where we now have to establish whether we can do it in one of two ways. Either the 4 minus 10 minus 21 is on the first line, or the minus 104 is on the second line. If they share a point, right? If they're parallel and they also share a point, then it means that they're the same line. Okay? So that's what we need to do next. So let's find out how do we do this. So let's take the minus 104 and see if it's on this equation down here. So we're going to see if this point is on the second line. Now, can anybody remind me in the 3 minutes that we have left, how can we establish whether that point, the minus 104, is on the line represented by the 4 minus 10 minus 21, m, that with that value? Put it into the parametric form. Okay, okay. So let's see now. Let's put the second one in parametric form. So that means that we'd have that x is equal, I don't know if you're going to be able to finish this, x is equal to the 4 minus 2m, and z, so I don't know where we're at z already, y. So always happens when I start to rush, that y is equal to the minus 10 plus 4m, and z is equal to the minus 21 plus 10m. Okay? So we started off with putting it in parametric form. That's good. Now we're going to take our x value. Remember, we're trying to see if this first x value is going to fit into this. So I'm going to say minus 1, that's my x value, is equal to 4 minus 2m. Right? I'm just taking the x value from here and putting it in the parametric form of the equation. And I'm going to take that 4, I'm going to take it from this side. So that means that minus 5 is equal to minus 2m, and therefore m is equal to 5 over 2. Okay, now we're going to use that as our m for the other points that we have. So let's go over here now, and let's see what the y value should be. Our y value, with that value of 5 over 2, should be equal to minus 10 plus 4 times 5 over 2. Right? That's what it's supposed to be. So minus 10 plus 2 into 4, that's 2 times 5. That would be plus 10 is 0. That checks out, right? Because the middle coordinate of that, the y coordinate, is 0. That's not enough, though. They all have to match up. Let's get to the z. I only have 1 minute left. The z should be equal to minus 21 plus 10 times 5 over 2. I mean, that's your m value. 2 into 10 is 5. 5 times 5 is 25. So that's minus 21 plus 25, which looks to me like that should be equal to 4. And does that check out as our z value? It does. And that's all she wrote.